Thank you very much. I really appreciate the invitation to be here to talk to you a little bit today. As you heard, I run the Almaden Research Lab, which is about 25 minutes south of here, about as south in San Jose as you can get without actually leaving San Jose, but a beautiful mountaintop location. And we do a whole variety of things around AI, quantum, cognitive technologies, hardware, software, chemistry. What I want to focus on today is some of the stuff we're seeing on the future of computing and with a hardware focus. So we'll talk about the applications that are driving this, but a little bit more about what that means from the hardware world. Partially because that's what I like, that's where I came from, but partially because I think it actually is a really interesting turning point we're coming into right now in terms of how we think about hardware. So just stepping back, when we think about technology in general, whoops, let me see if this is on. There we go. Technology is always about augmenting human capability in the end. So whether it's so we can communicate further away, see further, or communicate with different machines, be able to actually compute things that we couldn't do ourselves. It's always about finding ways to augment human capability to do things at scales we can't do. So the question is that what today do we need help in augmentation on? And I would argue that it really is data that's making the change in terms of why we think differently about computing today. So you've probably seen some version of this chart, the growth of data over time. I think the thing that's interesting, obviously 50 zettabytes is a very large number. It's 21 zeros if you want to actually write it out. But the type of data that's coming in is very different, right? So the enterprise data on the bottom is what we've been used to dealing with. And this is data like in databases, right? So it's in your databases, in universities, in government databases. It's structured, it's largely numerical in text, and it's, for the most part, well-ordered and easy to search and get information out of. Most of the growth, though, going forward is a very different type of data. So voice over IP, social media data, which includes a lot of pictures and images and videos, and of course, increasingly sensors and devices in the IoT space. So this is largely not text and numbers. It's certainly not structured or organized in any fashion. And maybe even worse, if you look at that white line going through it, a large percentage of it is actually of unknown veracity. It's not clear how accurate it is. If you think about, in your database, most stuff is pretty accurate. And you can make a mistake, but it should be fairly accurate. How accurate is your average tweet that goes out? Not particularly accurate depending on the source. But nonetheless, you want to take that information and somehow use it to actually find patterns and find things that are accurate that you can actually do something with. So what can we use to do this? Well, artificial intelligence is, of course, what people have been focused on. And I think the good news on artificial intelligence is it does work now, at least in narrow cases, right? So we can do fairly good language translation. We can do fairly good image recognition, object recognition, even in videos and moving things. We can understand language. We can do transcription from speech to text. So the ability to actually understand data that's not structured, that's not just words and numbers, is actually advanced quite well with AI. I think that's the reason people have gotten so excited about it. Now, I want to be clear, I'm talking about specialized AI, by which I mean applying it to very specific tasks. This is very different than, say, generalized AI, having an actual intelligent, or whatever that means exactly, intelligent system that can think the way a human can. And I think really for the majority of this talk and what I think is going to happen for the next few decades, this is the kind of AI we're going to be dealing with. So things that can do certain projects very well, but certainly not be a sentient being in any sense. Now, to run this AI, of course, you need hardware. So thinking about the context of where AI comes in, it's not just sort of one thing. The cognitive and AI bubble is, in a sense, a very broad area of machine learning, text analytics. It actually overlaps with big data and advanced analytics, which we've been working on for a while, but it also has some subcomponents of it. So if you think about the outer end, particularly the big data analytics side, it really runs on fairly large CPUs, large systems, HPC systems, server systems. If you look at machine learning, so now we're going to do something that is machine learning, but let's say rules-based machine learning. So something that's more handcrafted by humans to actually go do the understanding. It can still run on CPUs. FPGAs and GPUs can help there, but because the patterns of actual running are somewhat variable, they aren't as much of a help. But where there's a really big help is in deep learning. So if we talk about deep learning and neural nets, the patterns of understanding of what actually needs to be done from a workload perspective is quite clear. So GPUs are incredibly useful for this. FPGAs are very useful for it. And we're increasingly seeing people think about building ASICs, so very dedicated devices to go and do this kind of learning. So just to be clear on what I mean by neural nets, I think most people know what a neural net is, but basically the idea of a neural net is you build up a layer of nodes in a system, you put inputs into one side, and each node does some sort of nonlinear function on it, and then sends its output to the next layer of nodes. And the next layer of nodes collects all the inputs from the first layer, makes another function, moves forward. The idea is that from the input layer, you should activate just the selected output layer that gives you your answer. So recognizes a face, recognizes a word. So if you look underneath the covers of this, what this is largely is very large matrix multiplications and lots of matrix multiplications back and forth. So that's the reason it's actually quite amenable to automating as a workload, and it's why GPUs are very good at it. GPUs are very good at that kind of multiplication, not because they were ever doing neural nets, they were doing graphics acceleration, but it turns out the math is very, very similar. So therefore, it actually is quite useful for doing it. The other thing to think about with neural nets, though, is there's sort of two aspects to a neural net. One is the actual training of the neural net. So when you get a neural net to go do, say, image recognition, you have a blank set of neurons that have no particular weights or functions on them. You introduce an image into it, say cats or dogs, and you put it through. And at the end, if it sees a cat's image and says cat, you say you're correct, and you reinforce all the weights in that network. If it sees a cat and says it's a dog, you say you're incorrect, and you go decrease all the weights in the network. And you do this process back and forth several millions of times, if possible, to actually be able to go and get the thing trained correctly. To do that is very data intensive. It tends to run in big data centers, very memory intensive. You need large numbers of images to go after, and it can be done offline. You're doing the training until you get it so it's always accurate along the way. Once you have a trained network, you can actually then run it just in an inferencing mode. And in this case, you aren't trying to change any of the weights or change any of the programming. You're just showing it an image and asking it, is it a cat or is it a dog? And it gives you an answer. Hopefully it's giving you right answers all the time because you've trained it well. If it's not giving you right answers, you could always go back and try and retrain. But the difference is on that case, then you don't necessarily need to do the forward and backward passes, the various mechanisms to actually readjust the weights. So you don't necessarily have to have the huge amount of data. In fact, you might want to just do one image at a time, and your real goal might be to do it very, very fast, right? So as fast as possible to recognize that image is a cat or a dog. And you also might want to do it at the edge of the device, not necessarily at a data center. Maybe you want to do it in your car or on your phone. So you might actually throw some stuff off the chip to do inferencing more efficiently. But in the training side, you need to have all the math power available, all the memory available to actually run in the data center. So keep those two in mind, and we'll talk about both of them as we go forward. So I said that things are getting really good with AI, and just an example of what I mean. If you look at image recognition and speech recognition right now, you can see that up until, say, the late 2000s, we basically were running around 20–25% error rates, and this has been the case with neural nets since they started using them way back in the 80s and 90s. And then something interesting happened where suddenly they became really good. In fact, you can see the error rates drop in both cases precipitously around 2010, 2011. And it really is because two things happened. One is there suddenly was enough data, digital data available, that you could actually train them accurately. You want millions of images. So systems are really good at finding cats on the internet because there are a lot of cats on the internet, right? So there's sort of a self-fulfilling prophecy there. But the other thing that happened is GPUs. We started to understand you could actually run GPUs in very, very large systems, so you had enough compute power to do the training, because it's not trivial to actually do all the math necessary to train the networks. Once you had those two things in combination, you found that the error rates could be reduced quite dramatically. And in fact, today, the best neural nets out there can actually do better image recognition or speech recognition than humans can. So they've actually surpassed us on these very specialized tasks. So that's why we say with confidence it actually does work. The question is now, where do we go from here? So if we look at the hardware that's involved with AI, originally it was ASICs and FPGAs playing around with it. Suddenly people realized GPUs could do it really well, and suddenly you have something that's a fairly inexpensive device, relatively speaking, that you can put out at very large scales in giant data centers, and you could actually go and do stuff with it at very large scale and build large systems around it. Now, when you build those systems, though, it's not just the GPU that matters. It's the actual communication with that GPU that also makes a big difference. So this is an example of a system, the Power Minsky system from IBM, which has the PowerPC as the control CPU, NVIDIA chips for the GPUs, and you can see the bandwidth numbers there, 40 gigabits per second back and forth between these, and dual channels in many cases. The amount of data that needs to get moved in and out of these systems to actually do training and inferencing is really quite massive. And if you don't have this kind of bandwidth capability on it, the problem is you can't really scale up to really, really large networks, because that's actually, it's, as we know, even things that are parallelizable are only parallelizable as long as everything grows at the right rate. So in this case, this system here, we actually showed that you could actually scale it really quite accurately. So if you look on the right-hand side, we kept adding more and more nodes to the system to do training on the I think this was on our ImageNet, ResNet, which is a subset of ImageNet data set. You can see the ideal scaling would be the orange line, and the blue line below it was the actual scaling we got. So what this shows is by having really high bandwidth between the systems and having ways of adding the nodes accurately, you really can get to extremely uniform scaling and therefore go to very, very large neural nets. So that actually has changed even when we think about supercomputers now. So this is a supercomputer that was done by IBM for Lawrence Livermore National Labs, and it's got not just the large number of CPUs you'd expect, but actually has 27,000 GPUs integrated with it as well. Because now when we think about HPC and what we want to do with high-performance computing, it's not going to be just the really high precision work, which will continue to, of course, drive a lot of our workloads, but also very, very large neural nets, very, very large sort of AI systems as well. So building up those systems in a way that actually is scalable and actually is a way to actually take on big problems efficiently is a challenge from a system architecture point of view. But I want to go a little bit down below the system architecture. We'll continue to push that, of course, going forward. But one of the things that, of course, drove the semiconductor industry for so many years was our ability to follow Moore's law and continually improve our performance on our general purpose CPU chips. And of course, it was the 2x per year, 2x per 2 years, depending on the time you're looking at. So is there a way that we can do the same thing for continuing on workloads like neural nets, right? So GPUs is what we've been using so far. And this is a plot of a bunch of different GPUs and FPGAs over time that we just did empirically to see what looks like the trend we're seeing here. And the trend seems to be about 2.5x per year that we've been able to achieve as an industry at the chip level by continuing to progress those architectures. The question is, how do we keep that going forward, knowing that Moore's law itself is not going to help us as much as it used to in the past, right? We all know things are slowing down in terms of our ability just to shrink chips. So what can we do instead to actually make this continue on for the gigaflops per watt path? So what we think, and I'll talk about for the rest of the talk, is we'll continue to use something that looks like a GPU over time. But we also will start to look at more approximate systems. So those are systems that maybe aren't as accurate as what we do for high performance, high precision kinds of computations, but maybe are good enough for what we need to do for image recognition or kind of AI tasks. We also think there'll be a new rise in the need for different materials and devices. It's not clear that a digital silicon transistor is necessarily the best way to do the particular kinds of algorithms that you need to do for AI, particularly when you think about the fact that you have a ton of data you're trying to move through that. So in a way, you'd like to get that data closer to the compute and actually do more in-memory computing. How could you do that, and what kind of devices might help that? And then I'll briefly also touch on the last part of the talk, quantum computing, which is not necessarily for AI, although it actually probably will help certain AI problems, but is also another way of actually augmenting what we're doing in the hardware space for a specific set of problems that we see as growing in the future. So starting at the top, what do I mean by reduced precision? This picture on the right-hand side here, or left-hand side for you, sorry, is I'm guessing you can all recognize, even though it's obviously a very low resolution picture, has a lot of errors in the bits. I don't think anyone has problems figuring out it's the Mona Lisa. So that's why we mean that in this kind of context, it's not clear you need to have every single bit right to get the answer, which is Mona Lisa. So the very first thing we think will keep us going, and this is the point we're putting there is a point that we think we'll be able to achieve in our AI center work that we're doing. It's mostly coming from just a reduced or mixed precision. So here's just an example of what that looks like. So on the left-hand side here, this is training errors and test errors on the right-hand side for different rounds of training on the system. And the black line is if you use floating point, really full-on 32-bit floating point. That's the way it gets trained off. You see if you reduce that to 14-bit floating point, the red squares, it's really not that much different. So you actually reduce your precision by almost a factor of 2, but yet it still actually trains pretty well. In fact, even the 10-bit floating point seems to train reasonably well. You're getting a little more error there. Now when you get down to 8-bit floating point, the green, you aren't training as well anymore. The errors, you aren't really able to converge and get down to the low error rates anymore. But what this tells you is that you can easily at least get a factor of 2 just by reducing the precision of what you're doing on the chip. And there's no reason it has to be 32-bit floating point if you're using the GPU strictly for actually training the neural nets themselves. So that might get us a sort of one step forward. But what if we took that even further along? What if we said, well, if I don't really care about precision, could I go back to analog at some point? I mean, analog has a really nice ability to do lots of different levels if you don't care exactly where that level is in between. We do think so. So we think that maybe the next step beyond this might be to actually produce an analog style chip. And there's going to be 2 advantages to having it be analog. One is the precision, but the other one I want to point out is if you go to analog in a cross-point structure, you may be able to also avoid part of the problems we have with moving the data around in the system, right? So right now, the memory, of course, is on one side. You have to move it in and out of the compute, whether it's GPU or CPU. In fact, sometimes that goes through the CPU to get to the GPU, which is horribly inefficient, but that's the reality of the way these things run. It'd be really nice if instead you could actually have it happen in the memory. So by going to analog and a cross point, we actually think that that's very doable. So just to remind you what the actual neural net looks like. So one thing you can see is the first row of neurons. Every neuron there connects to every neuron in the second row, right? So if I put up a cross point, you think about the left-hand side, those pink things being neurons in the first row, and the pink boxes on the lower part being the neurons in the second row. A cross point will allow you to connect all of them together. Now, what do you actually want to do as you connect them? Well, it's basically just a multiply and add, right? So that is exactly what you get if you take this circuit here, you flow current through a variable resistor in that unit cell and take it down there. You'll get the sum of all the currents based on the resistance in each of the unit cells. Does this work? I don't know if this is going to work or not. So if I take these as variable resistors in that first row of unit cells as those connections, I'm going to get the sum of those currents in this next neuron based on the different resistances that are in each of these cells. So you basically just did an analog computation that takes into account everything that came from each of the neurons through. But you did it without actually doing any math, which is, of course, really nice. So this is the reason, and the basic structure we think that can actually push things forward from an, what we call an RPU, or resistive processing unit type of memory. Now, fortunately, there is a material that does this. I think we're all familiar with phase change memory, which is right now, of course, used for maybe doing multiple states for solid-state memory. But it's basically an analog resistance in the end. And we don't necessarily want to use it that way all the time. But for this, we actually want to do exactly that. So we built an array of phase-state memory, just a fairly small array, and actually used it to try and train on the MNIST data set. So the MNIST data set is just integers, handwritten integers. So a fairly simple image recognition. And you can see that we actually were able to get about 82% accuracy with 5,000 examples that we trained through it. Now, the actual full data set is 60,000 examples. We couldn't actually do it on the original one because this was too slow. So it turns out that this question of speed and analog still has to be worked out along the way. But if we were able to get to more examples, the question would be, could you actually get to this sort of 97, 98% state of the art with the same thing? And we actually just did do that just about 2 months ago. We were able to get a more efficient system for running it. It's actually had more to do with the peripheral circuits running things in and out of it. We were able to train on all 60,000 examples, and we were actually able to get up into the 96, 97% accuracy rate baseline, or what you can do best of is about 97 to 98%. So well within the range of what you can see. And this is all analog, right? These are just variable resistors in a cross point. So this question of whether or not the precision there necessarily is necessary to get to the answer precision is clearly not the case. You can live with very low precision in the actual individual units and still get a very high precision answer in the end. So if you think about that, we'd like to go on and continue on with the analog accelerator, get to the next point. And this point right now, I will say is I won't call it a fiction, but I will say it is our best guess as to what we'd like to be able to get to in that time frame. But in order to get there, we really do need to improve this resistive memory. So phase change memory is what we're using right now, and the materials there were optimized for the usage that we had for memory. That's not exactly what you'd like to have if you're going to use a material for using this as a variable resistor in an actual neural net architecture. So we actually published a paper that talks about what you would actually like ideally in terms of characteristics in a material to be a good analog resistor for this memory, or for this neural net application. And lots of things there. The one I want to just point to in particular is you've got to have the device asymmetry there at the bottom has to be very, very linear. Don't worry about storage capacity. For some reason it's, well, You want to have about 1,000 levels. You want to have a lot of different steps you could take in it. But more importantly, you want it to be very linear up and down. So every time you give a pulse to actually change the resistance, you want to be sure it's going to give you the same amount of resistance change. Understanding this is analog, so the same is not like 32-bit accuracy here, but you do want a very nice linear structure. And that's the biggest challenge we see on these materials right now. If you look at a standard device here, the blue dots on the left-hand side, it turns out that standard phase change memory is quite linear in one direction when you're trying to go towards the high resistivity or high conductivity mode. When you want to go the other way, it jumps right down. It's very nonlinear the other direction. Now we have gotten the ideal RPU would have the red dots that you see there. We have not achieved that yet, but we have achieved a material that's looking much better. So this does have something where you can do 1,000 steps up and 1,000 steps down, and it looks somewhat linear along the way, not quite as linear as we'd like, but at least it's showing that there are things you can do and play with to improve these materials. So since my background is material science, I really like the fact that materials are back in vogue again. So we're actually working a lot on trying to figure out how you can actually continue to improve that kind of characteristic. I think the other thing which we're thinking of further down the line is this is great if you're going to just do a cross-point memory and use it as a resistive element. Are there things you could do that would be more interesting than that for actually doing the training on a neural net? In which case you might want to have more interesting functions that are being produced analog. That I think is actually more of a research area right now on the software side, figuring out what you actually might want as a different way of training your algorithms. But I think that if we learn how to do this right on these materials, that opens up the door to other types of structures in the future as we learn more about better ways to train systems over time. So I've talked a lot about training. I want to talk just a bit about inferencing. So I mentioned that inferencing is something that might not happen in a data center. It might actually happen on the edge. And there's good reasons for it. There are lots of things we want to do where we want computation to happen actually on site. So obviously, self-driving cars. Huge amount of data created all the time. If somebody walks in front of the car, it has to react in about 200 milliseconds in order to stop. It doesn't matter if the cloud figures out 10 seconds later it should have stopped. That's not very useful, at least not for the pedestrian. So it does have to happen actually on the car. Mobile devices. So in this case, you might not need to have instant gratification in terms of timing, but you certainly don't want a large power sink, right? You've got your phones are only a couple watts. You don't want to be sucking down the power too much on those. And you also have a lot of sensors, so a lot of interesting things you could integrate and actually get some information on it. If you had a way of doing it locally versus having to go to the cloud all the time, you could actually open up a whole new application space, or at least there'd be less of a delay when you talk to Siri, which is kind of annoying. Even something like security cameras, where you actually have plenty of power now, so that's not a problem, and you're hooked into a wire, so you can actually send it back to the DVR. That's great, but that is exactly what happens with security cameras, right? All the stuff just gets sent to some DVR. If the next day they find out that somebody stole something from the Walmart store, then they go try and find the DVR, try and figure out who was there. Of course, by then they're long gone. So the best is going to help you if they ever come back in the store again. What you'd really like is to have the DVR camera itself be looking at it and saying, hey, wait, something weird is going on in aisle 14 right now, so go look at this. And you need the camera to do it itself because you can't take all that information back, analyze it all back in the cloud, or send it all back to some poor security guard who's got to look at all of it. But the security guard can't look at one if you send them that one bit of information. Or at an ATM, if someone's sticking their card in the ATM, if the picture on the card doesn't match the face you're seeing in the security camera, it tells you immediately there's something going on, and that alert can be sent back. So there's a lot of good reasons to get inferencing chips there. We did look at a sort of the ultimate version of an inferencing chip called True North a couple of years ago. This is a spiking neural net, so it cannot be used for training at all. You train on data center systems using GPUs. When you have the trained neural net, you actually map it onto this spiking neural net system. And it can now do a million neurons, 256 million synapses for only 70 milliwatts. So a very small power budget compared to what you see in data centers. Even your phone is a couple watts, so this could, in theory, be on your phone and still actually be always on paying attention to things. Now these are all digital, by the way, these are just digital neurons and creating a spiking neural net. I'm not going to go into details on what that is, but basically you can think of it as being 1-bit precision, so literally the lowest precision you can imagine in terms of actual neuron-to-neuron communication. So that's the reason we really push to get to the lowest possible power. And the interesting thing is it can actually do all the same things that we saw the other systems could do. So this is a camera actually on top of the Hoover Tower at Stanford, and the task was to find and track cars, bikes, and people in real-time video. It's the same problem on the other side, except you're in a helicopter now, so that the background's moving, so it's a little bit harder. But this is doing 3-color, 30 frames per second, real time, no latency recognition on those chips. Now this is, to do that whole picture, it took about 16 chips, because it's not a very efficient neural net system right now. But that's still, 16 chips was still only a couple of watts, right? In fact, actually, the amount of power it took to run the FPGA, which was just translating the signal from the camera into the neural net chips, was actually much higher than what the actual chips themselves were. And of course, it could do any other type of algorithm you might want to actually put on it. One this audience might be interested in is actually we did a partnership with Samsung down in our Almaden Research Lab on this, and they hooked up a system with what's called a retinal camera. So it's a camera that doesn't just show full images, but basically just fires like the way your eyes fire when it sees a change, a light change or an image change. It just fires for that purpose. That's hooked, so it's spiking, right? So that's exactly what that is. It hooks directly into the neural net of our chip, and they were doing it for hand gestures for controlling a game player in this case, or sorry, a TV. So volume up, volume down, change channels, change images. The thing that's nice about this versus like your Kinect or something, there's no special light source needed, right? This is just a camera sitting there on the deck or on the TV screen, on the TV platform, looking at you in normal light. So you don't have to have a lot of the other stuff that goes along with most motion detection kind of systems. You can also use inferencing chips at very large scales. If you want to go up to, we talked about the supercomputers with GPUs. We actually did a 64-chip array for the Air Force Research Lab of this, because they're building very large neural nets at the inferencing levels. And the thing that's interesting about this is about 10 to the 8 neurons then at this point that's going on there. Because if you really want to get to brain scale sets of neurons, that number of neurons, even with GPUs, that's too much power for your average data center. I mean, we did some estimates that if you really wanted to just go through and simulate the number of neurons in the human brain and number of synapses, it was going to take something like 12 gigawatts, which is big, even for a data center, to say the least. It's a couple cities is what that is actually. So you do need to actually get to very low powers if you want to get to that scale of neural net in the future. And I would say, by the way, that when we simulated that brain, it was not a brain. It was just literally simulating that number of neurons. And we actually did it at 1,500x slower in order to make the power only 8 megawatts at the time. So we have a long way to go to get to brain scale. I'm not too concerned about that yet, but we do need to think about power for that as well. So we've talked a lot about neural nets and hardware and how they can continue to help us scale to more and more advanced problems there. There are other sets of problems, though, that are also challenging us right now that are not necessarily just big data, but different types of data. And I'm going to start this section with a quote from a physicist, Feynman, Richard Feynman. It says, "Nature isn't classical. Damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy." And he said this actually at a meeting at IBM back in the early 80s when they were first starting to talk about the idea of quantum computers. And his point was that there are certain problems that are just so hard to do because they involve so many quantum states or other types of states that you just can't do it on a classical computer. And just to give you an example, let's suppose you wanted to study the molecule caffeine. A molecule we all love a lot. Probably some of you are drinking some of it right now. It's a fairly small molecule. It only has 95 electrons. If you wanted to actually do a classical calculation, 10 to the 48th classical computer bits would be necessary to actually represent all the possible quantum states of just this simple molecule. So we just wrote that out to show you what that looks like. That's because each of those electrons can interact with every other electron, and they all are quantum. They all can be in superpositions and entangled. So you actually have that number of classical bits that you need to do. So is that doable? Well, the number of atoms in our planet is about 10 to the 49 to 10 to the 50th. Seems a bit hard to figure out how you get 10 to 48 of them to help you do this particular one molecule. So clearly, you will never get to certain problems using classical systems, no matter how large the system you build is. So what if we went instead to using, the key point here is if you did this with qubits, 160 qubits, 160 quantum bits would be necessary to do this molecule. That is very achievable, and we'll talk about where we are today on it. So why is this? Well, interestingly, at a high level, if you think about what we did with classical computers, the performance of the computer scaled roughly with n. Famous Moore's law, right? You double n, you double the performance of the system. Now, we know there's a lot more complications underneath the covers, but roughly that's the case. If you think about a quantum computer, every time you double the number of qubits, which is the closest we're going to have to an equivalent to a transistor, you actually raise the performance of the device by 2 to the n. So that's an exponential growth now, right? So that's a much different kind of scaling than we're used to in the past. And this is the power that allows quantum computers to actually go after certain problems. And when I say certain problems, it's not going to run PowerPoint for you. I mean, this is very specific problems that you can go do no other way that are mappable onto a quantum system. And the things that give you this capability with quantum computers, one is the superposition principle. So in a normal bit, a bit is a 1 or a bit is a 0. And hopefully it stays 1 or 0 all the time, right? Memory companies know it's very important it stays 1 or 0. Qubits, on the other hand, can be in a superposition state where they are partially 1 and partially 0 at the same time. It's just a linear combination of the two potential states they could be in. So I have a probability then when they're measured of being 0 or 1. When you measure them, they will always be 0 or 1. But the probability of whether you're going to measure a 0 or 1 can change depending on the superposition state it's in. And that basically allows you to test a much larger space at the same time. Instead of testing a 0 and a 1, in a sense you can test both at the same time. So it's kind of massively parallel. It's not exactly what happens, but it's roughly a good way to think of it. The other thing that's important to know about qubits is they can be entangled. So you can take two qubits next to each other and entangle them in such a way that when you measure one, it actually determines the behavior of the other. So you actually get a controlled knot, for example, or some other controlled information. So now you've got not only the ability to do superposition for each individual qubit, but you can entangle it with every other qubit around it. And you start to do the multiplication on this. This is where these numbers of quantum states come in, and why you get the 2 to the n kind of multiple on it. It also means you need to be able to map your problem onto something that looks like this, that looks like a multiple set of states exploring a very large phase space, in a sense, of the answers that could possibly happen. The reason it's so good for quantum chemistry, which we talked about earlier, is because, of course, that's exactly what the electrons are doing. Electrons themselves are quantum entities that are in superposition states that are entangled with each other. So in a sense, you're just doing a one-to-one sort of mapping between these two things. But there are lots of other problems that could also be done by this, which we'll talk about. One thing to keep in mind, it's not just the number of qubits that are going to matter, however. The biggest problem with qubits is that they are very fragile entities. They don't actually maintain the superposition state for very long periods of time. Currently, I think our record is about 90 to 100 microseconds of coherence time on them before they basically decohere and you get an error. That sounds really short, but that's really long for qubits, so it's a very impressive number that way. And also, if you think about electronics, we do things in nanosecond scale. So microseconds actually is a long period of time to be able to do actual computation. But if you want to continue to progress, you not only need to increase the number of qubits, but you have to increase that time, the ability to have lower error rates. So we talk about actually doing quantum volume as a way to measure how big a quantum computer is becoming over time. So if you sit at 50 qubits today, if you were to just double the number of qubits to 100 qubits, but didn't increase your error rate, or improve your error rate, you actually would find you get no ability to actually do any larger problems. You would actually not be able to do anything more than you could do with 50, because you're actually limited by the error rate and the communication time between them. On the other hand, if you stayed at 50 qubits and actually decreased your error rate by a factor of 10, you'd actually get a 500x improvement in terms of the size of problem you could actually go solve with this. So when we're talking about advancing the quantum computing problem, it's both of those that are important. Increase the number of qubits and increase the error rate. And the reason that's important, I think, for people who think about materials and semiconductors is error rate's all about getting things really, really quiet, right? So obviously we can get it cool, we can isolate it, but there are traps in materials, things give off ions. So there's all sorts of interface effects and things that we're studying to understand what makes the error rate what it is today. What is it going to limit us? Now, what we use for a qubit today is a Josephson junction, which some of you guys might remember from the RSFQ days. But it's basically a thin barrier between two superconducting materials. You can then put it into superpositions of states between ones and zeros by sending in RF frequency. So basically, you're sending in microwaves to actually set these systems in different positions. So it's not at all digital. Nothing at all that sounds digital about it anymore. It's really very much an analog and RF process. So we actually have built these systems. This is an example of one of the systems in our Yorktown Heights lab. There's also some in the Almaden lab up there. That's the dewar they're putting over it to isolate it itself. It's got to be kept at very low temperatures along the way and very isolated from any kind of electronic noise. But if you get and do this, you actually can get some systems that do some amazing things. So this actual picture here is a picture of the 50 qubit system with the cover removed now. And just to be clear, the whole computer is this little chip that's down here in the bottom. All the rest of this is the refrigerator and the signal routing, because you have to isolate things down and you have to be able to get signals in and out. So the diagram on the left, which you won't be able to read through, basically each of those plates as you go down is getting colder and colder in temperature. So the very top plate is actually at 4 Kelvin, so a very balmy 4 Kelvin. You go down to about 200 millikelvin, 80 millikelvin. By the time you get to the bottom, we're actually at 10 to 15 millikelvin. So that's 10 to 15 thousandths of a degree above absolute zero. So for all of us non-physicists, that's 0. It just sounds like a rounding error. For physicists, I'll tell you, 15 is important, 20 is crap. So you got to be really careful. So anyway, we spent a lot of time getting it just right to get the error rates nice and low. And you can see all these lines here, which are, it's a beautiful piece of equipment, by the way. It's probably the most beautiful computer I've ever seen. But it's all for a reason. All those little lines that you see, those are coax lines to bring down the RF signals. They're looped because, of course, there's expansion problems when you're cooling and heating. They go through some very carefully designed noise insulators right at the end, because you're going to take that signal in to 15 millikelvin. You want to put very little energy in. You want to put no noise in. But yet you still have to get the signal in to flip the qubit. So it's a really complicated engineering problem to actually make this happen. But if you get it to happen, you can actually do some really interesting things. So analogous to the diagram I showed on machine learning and cognitive, if you think about just the realm of problems that one can solve with computers, there are easy problems that can be solved. There's a whole class of hard problems for classical computing. So the kinds of things we do, like when we try and do predicting the weather or trying to do large simulations that we use HPC systems for today. But there are also some problems that are outside of that. They're even harder, as we said, like the caffeine molecule, that they may be quantum possible. That is, you could actually do them with a quantum computer. So we mentioned chemistry already. Also optimization problems, so like think traveling salesman style problems where you have a huge number of options to actually go after. You can map that on. Machine learning, it turns out, again, if you've got a very large phase space, if you think about a neural net, in some ways it's just trying to divide things in different sort of vector spaces. You can think about mapping that onto a quantum computing problem as well. So we think that there'll be some applicability there as well. The other way I didn't actually show on here, which I think everyone thinks of first, is cryptography, of course, right? So encryption and being able to break the internet, as they say. So a couple comments on that. First of all, in order to get a system that could actually factor any number that would be of interest to us, you have to have millions of qubits. So we're at 50 today, so millions is quite a leap along the way. And you have to get the error rates down along the way as well. And if you actually had a system that big, there are other forms of encryption we could be using that actually aren't breakable by a quantum computer. Right? There's nothing that says a quantum computer can solve every problem. In fact, actually, at our Think conference 2 weeks ago, we talked about lattice cryptography, which is another way of doing cryptography, which you can use today. It's a bit overkill maybe today, but you could use it today, and that's not something you can break with a quantum computer. So this concern about quantum computers breaking the internet is really far overblown, both in time as well as reality. And we also believe there's a lot of other problems you're going to be able to solve much earlier on. And in fact, on the quantum chemistry side, we actually published in Nature just last year the ability to simulate very small molecules. So these, obviously, you can simulate these on a normal computer as well. But it does prove out that even with a few qubits, this was only a 7-qubit machine that was doing this, so a very small number of qubits, you were able to get the simulations of these molecules correctly. So this does prove that if you can get a system large enough, you can start to actually do stuff with it that you can't do on other classical systems. In the case of chemistry, if you get to about 50 to 100, maybe a couple hundred qubits, you'll be able to do problems that you can't do any other way. So we are not that far off. We're at 50 today. We're not that far off from actually seeing actual value from this in the next 3 to 5 years. So we actually released an the IBM computer on the quantum computer on the web in 2016. IBM Q, you can Google it up. It's an actual quantum computer running in the basement of Yorktown Heights lab at 15 millikelvin. There's a great set of tools and simulators. You can run a simulator. You can also run the system itself. It's got it was originally a 5-qubit system. It's now a 16-qubit system that we actually have released for everyone's use. It's got a nice set of software tools on there as well, both a sort of a graphical tool for dragging and dropping the programming, but also starting a whole open source software kit to actually start building up libraries. And if you go out there, it's fascinating to go look at it. They're great tutorial videos for one thing, so you can actually learn about it if you aren't a quantum computing expert, as I was not. And also you can also see what other people have programmed on there. And it's a great set of libraries to go play with. And we really have it out there because we need, if the world's going to do quantum computing, we need everyone to understand and start using it. And this is one of these things where the whole ecosystem has to start to think about what kinds of algorithms can we run on it, what's the best architecture to use, all these sorts of questions we hope to answer by having this be very open. Actually, Samsung has joined us in our the commercial version of this. We launched in December the IBM Q Network, which then has access to larger systems, as well as other libraries and tools that we've got. So Samsung was one of the partners that joined us on this. Interest, obviously, from Samsung is probably in things like materials discovery, chemistry discovery, right? Can you simulate some of these things for future devices in the future? You also see some banks joined us. Financial transactions are very large optimization problems, so obviously they would love to get a way to do that faster. And even a car company, and in their case, they're thinking about if you get to self-driving cars, the traffic routing problems you're talking about and the ways you're going to interact with large numbers of cars in the systems, again, something that's fairly amenable, we believe, to quantum computing. We also just had an event. We've actually had a bunch of startups that are starting to use this stuff as well. So I do encourage you to go take a look at the IBM Q site, even if you aren't an expert at it. I think it's important for us to all at least understand a little bit about it and where it's going. It's coming a lot faster than I think any of us thought, even those of us who've been working on it. So I think it's actually one where keeping on top of it is an interesting challenge. So with that, I'll go ahead and wrap up my talk. I think the key message I want to try and get across here is, as we enter in this next era of computing, in some ways it's going to get interesting again for the hardware guys. I mean, which I'm a hardware guy, so I like that. It used to be it's all about apps and software, and there's still going to be a lot of that. But I think to actually do some of the stuff that we're going to find really exciting in the next few years, getting new system builds, getting new chip builds, even getting new materials and devices is really a big challenge, and it gives an opportunity then for companies that have kind of the full stack of those capabilities in-house to really make a difference and maybe get some advantage in innovation. So with that, I'm happy to take any questions.
So thank you for a great talk. I had two questions. First is kind of a simple question about the power system you showed with the NVIDIA GPUs around it that was connected using NVLink, I suppose.
Yes.
So at most recent graphics technology conference, NVIDIA showed their own switch. And so a question that arose in my mind when I looked at that is that for a while, IBM Power Systems' position was that it's a great middle around which you can hook up things like peripheral memories and GPUs, and it's in the middle orchestrating. But do you think NVIDIA's strategy takes them away from where they need a power system in the middle for a multi-GPU system?
It really depends on what you're trying to do. I think, obviously different systems can be optimized based on what you're after. I think still having some sort of fairly powerful control CPU involved is actually helpful for certain problem sets you're doing and certain ways you're actually using the system, particularly if you're building really large systems. Yeah. So I think that you'll still see that need. Whether there's some systems that you can get away without using it, I'm sure there's be ways to do it, but the reality is you still need a control CPU that's got a reasonable amount of power if you want to take on big problems.
Thank you.
Yeah.
The second question is about quantum computing. But to what extent do you believe that the brain quantum computes? So there are, various theories out there, including some famous people like Penrose and so on, which is not clear to an outsider like me whether these theories are accepted, and indeed people are building modern quantum computers in the same way that some people theorized, that like Hameroff and Penrose, for example, is one theory. It's not clear if there is any lineage of ideas.
So first of all, I'm not an expert in this area, so I don't want to say that I'm saying exactly correctly. What we're going for with our quantum system is much more along the lines of the way you'd think of a normal system being. We're building universal quantum gates so that you actually can build a Turing-complete system that would operate the way we think about other computing systems operate, with, of course, the advantage that it has the superposition and entanglement to do problem sets that are much beyond it. So I doubt that has much bearing or similarity to the way the brain works. And I also it's not clear to me whether the brain actually is using very many quantum effects or not. I think that's actually still very much theoretical, but we certainly are not using that as our pattern. On the other hand, we're doing the AI and neuromorphic chips, like the True North chip. That was clearly inspired by the way we believe the brain actually operates and gets to low power. So it was asynchronous, it was just spiking, it was very, no external memory, everything was very much the way we think, or at least inspired by the way we think the brain might operate to get to the low power levels it does.
Thank you for your answers.
So there are obviously other companies that are doing, fair bit of work in quantum computing. Is there general consensus on the approach, in the industry? Are they all kind of architecting it the same way? Are there fundamental differences between how you guys do versus Microsoft?
Yeah. So the majority of companies, Microsoft, Intel, Google, ourselves, Rigetti, which are probably some of the bigger ones out there, are all approaching it largely with Josephson junctions and trying to build universal quantum computers that would be fault tolerant over time. There are some outliers out there. D-Wave obviously has a very different approach. They actually have a very large number of qubits, up to a couple thousand, but they are basically building what's called a quantum annealing machine, which is, it doesn't have full entanglement across all the qubits, and is, for people who have found advantage with it, it has advantage for very specific types of problems. It's not in any way Turing complete. It can't be mapped onto every other problem. We don't think it's actually scalable the same way that the universal system would be, but there are some people who are using that. In terms of other functionality, there are some people who are still experimenting with ion-based quantum computers, so you're using ions that you can put also into superposition states. Some people are working on optical. There's actually some fairly far out work. They're using different types of physics particles that you simulate in 2D structures that, if one of those came through, actually there's one in particular that actually would be really great if it turned out to be real, but long way to go on that. So I think most of us feel like the Josephson junction is probably the easiest way to go at it.
Let him ask and now come on.
Okay, yeah, definitely working at absolute zero is difficult to manage, I'm sure. Yeah. So I guess you partly answered my question about those alternatives, I guess, that people are seeking, but yeah. You need to be that cold because you have to have superconducting properties, and
it's a combination. So obviously superconducting is part of it, but you have to be that cold mostly from a noise perspective. So the thermal noise, just the phonons themselves, if a phonon hits the qubit, it will decohere. Basically, the rule of superposition is as soon as it gets measured, it has to be a 1 or a 0. And measure means interact with anything in the world, right? So it's not me measuring it, it's anything that interacts with it. So that's why you have to get all electrical noise, all thermal noise, everything away from it. Now there are some systems that are somewhat more robust. There's some syntronic systems that people are looking at that wouldn't have to operate quite as cold, but they still need to be fairly isolated in the end. I think one thing, quantum systems clearly will always be cloud-based systems. I mean, you aren't going to have it on your cell phone or anything because it's just, they're too fragile. But at the same time, most of the problems you want to solve with quantum computers really are more amenable to the cloud anyway.
Okay. And you'll make more computers available over time, I guess.
Yeah, exactly. That's the idea, is to continue to expand this out. Right now, I mean, if you go on the system right now, it's a 16-qubit system, and we have a 5-qubit and a 16-qubit both online right now. So you actually can get on either one depending on the size of the problem you're running. The Qs aren't that bad even for running the actual system. You also can run it in a simulator that can either be an exact simulator where there's no errors, or one that's fairly realistic in terms of the error rates. So you actually can do a lot of work on the simulator, which then has no Q at all because you can run as many as you want. So,
from a security perspective, you mentioned that there was some ways or algorithms to protect against large computers like this from attacking systems. Mm-hmm. Cryptocurrency kind of comes to mind as one of those. And there's some that are potentially quantum proof. I don't know if that's how true that is, or maybe you just need more qubits to attack it.
No, actually, I think I don't know exactly what the cryptography is they're using, but there are certainly ones I can think of you could apply to blockchains and Bitcoin that would be quantum proof. So it's certainly very possible to come up with ones that are quantum proof even for that. The reality is we use the version we use right now for cryptography on the internet was just the most convenient one to use. It was a good trade-off between computational intensity, speed, and security. But as we've got bigger systems, we've even done that and we've added bits, right? We started off with 64-bit, now we're at 128-bit. We add bits to that as computers get better. When you go to quantum, you just need to go, there are different techniques you can use that are hard for a quantum system to solve. And there's no reason we couldn't switch to them, it's just there's no driving force to do it until you actually have a concern.
My question here is now, in the last few years, because of the so many applications driving AI, so there's a huge wave of adopting GPUs in data centers. GPUs now also FPGAs, and they also mentioned there's a race to ASICs.
Yeah.
So is this race to ASIC going to become a really, really big wave? And how big a wave or torrent is that going to be?
So it's an interesting question because I think we are seeing a lot of startups out there that are looking at different ASICs. Yeah. I think I would kind of put it in two categories. I think for the training side, going to ASICs is the bigger challenge because of two things. First of all, GPUs are very good at training, so your bar is very high, so you have to get better than. And secondly, we continue to change the way we train. We're learning different ways of training neural nets. You know, we don't really, you know, the reality is no one really understands exactly why neural nets work as well as they do. I mean, they are in a sense a black box. The theoreticians and such, the Simon Center up in Berkeley, you know, they're looking at this all the time, but it's not really clear why they work as well as they do. So we're going to continue to evolve how we train them, I have no doubt, and the kinds of architectures we use. So building an ASIC that locks yourself into really amazing performance for a very specific way of training is a little dangerous. On the other hand, on inferencing, you know, there I can see more of an ability to do an ASIC, because you can train it any way you want to. In the end, if it's a neural net, you kind of know what it's going to look like, so you know how you can run it efficiently. That's the reason we went down that path with the True North chip initially, was how can you run a neural net really, really efficiently. So I think there's probably a little bit more room there. In terms of sheer volume over time, once everything stabilizes, you know, the number of inferencing chips you're going to need is going to be huge, right? You're going to put one in every sensor out there, you're going to put one in every car, all over the place. On the training side, it's probably more limited because you will almost always do your training in the data center itself, right? Because you want to have a large number of images. There will be those edge cases where you maybe have a robot that you want to have learn as it's going along, in which case then you will need to do training there. Although even there, how much training you do on the robot and how much you would still send up to do in the back end, the data center can be flexible depending on where you think the learning needs to take place. And you don't want your car learning while you're driving, so that's clear. You don't do any training there. So.
But Google seems to be very, very deep into using ASICs for TensorFlow processing. Is it a trending process also, or is it a? Yeah,
I think the TPU it's a good chip. I mean, I think it's you know, whether it's better or worse than a GPU, I think is I haven't used it enough to actually say. I'm guessing Google also uses a lot of GPUs out there.
Okay.
I don't know that for a fact, but I'm guessing they do.
Maybe a third question that now you mentioned non-volatile memory. How much memory would be meaningful on the chip for either training or inference?
So for training, the amount of memory you need is, you don't do it on chip. You do it like in fact, you do the stack memory, for example, because you certainly want to get into the terabyte kind of range if you can. Okay. For inferencing, you know, it's not clear you need much memory at all on chip for inferencing. If you're using a GPU for inferencing, then just by the way the GPU works, you are still moving a lot of stuff on and off the chip and from external memory. Like the way the True North chip works, you didn't have to actually do that. The model is already on the chip, and all you're doing is just streaming the data through. So you don't actually need any particular memory for it. It just can take it directly from a camera, for example.
Mm-hmm. All right, thanks.
Yeah.
Mm-hmm.
So one question on the analog computing: are you still sort of maintaining a von Neumann style, you know, architecture? Is there a computing and then, you know, memory and then a
yeah, it is. I mean, so it's the actual learning part. The cross point is obviously not von Neumann. There you've got kind of a mixture of where because the memory is the element and it's also the compute thing. But that would all be controlled by very much a normal von Neumann style for streaming the data in and out and all the control functions around it. In fact, actually, the work that's going on in Zurich, our Zurich lab, is actually looking at sort of an intermediate point. Before we go to a full cross point, there are ways you can put some analog devices in to help with some of the updates. Some of the forward and backward passes on the neural net, but uses more of the control network and high precision digital for doing updates on those weights. And we think that actually is probably easier to get to first. So in that case, it's almost all von Neumann, but you just have a very key part that's got a little bit of analog in it.
And then what's the largest, you know, that analog chip that people will actually build? And the reason I'm asking is, you know, obviously the larger these chips go, noise becomes a much, you know, intractable problem.
Yeah, I don't know the answer to that, how big it's gotten. I mean, we've gotten, you know, on the order of half a megabyte kind of thing, but that's not, you know, that's pretty small in terms of this stuff. And it's an interesting question how it will scale because, you know, if you're talking about just having the nodes in the neural net, in that case, the number isn't really limited by the error rates progressing because, you know, every time you go through it, you're getting your number down there. There's no reason it won't. You can continue to. You won't propagate those errors in terms of like timing errors or things like that. You aren't using analog for timing. You aren't using analog for any of the control signals. And if in fact, you know, this particular node gets slightly off on its resistance, that can either be adjusted back down in the process as we're doing the training, or the other nodes actually can compensate along the way. So I don't think there'll be a big limitation in terms of errors propagating on the cross point itself.
So where do you see then the practical application? I mean, obviously there are all these challenges, right? Do you see these kind of used in specific niches where, you know, the bang for the buck is just pretty significant, or are you guys envisioning this as becoming somewhat mainstream?
I think we're envisioning that it will eventually become more mainstream because what we're seeing right now is that GPUs do a really good job at training right now, and they've got a roadmap to continue to do a good job at training for a generation or two. But they're limited by Moore's law as well, right? And they aren't, there's no magic that's going to make them go much further. So that's the reason we think that you will, if you're going to continue to train larger and larger neural nets, you will need to have something that is lower power and higher performance. And analog is reduced precision, and then analog are really the only ways we see of getting to that point. And the only reason you can do it is because you're dealing with a problem that can live with the errors along the way.